Greetings, chem students. Today we're going to talk about reversible reactions. Okay? And our final objective after we learn about reversible reactants is to actually calculate the equilibrium constant. All right? Now, a reversible reaction is the conversion of reactants into products. We've dealt with that many times this year already. Okay? We've taken a certain couple of reactants and they make products. We've even predicted what products would be made when we talked about reaction predictions. Now, what we haven't dealt with is the simultaneous conversion of products back into reactants. So basically, we have a reaction that is going in two different directions. We call the first one, whoa, what's going on here? We call the first one the forward reaction, okay? So the conversion of the reactants to products is called the forward reaction. The conversion of products back to reactants is what we call the reverse reaction. So what I've done here is I've put this little reaction in here. I have two sulfur dioxide molecules as a gas plus one oxygen molecule as a gas will yield two sulfur trioxide molecules as a gas. You can see that I have a balanced equation, and if you look right here, okay, this blue symbol here is what I typically see for a reversible reaction. Now, I couldn't find how to put that into PowerPoint, so I just put the double arrow here, signifying that it's going both directions. Here is the forward reaction, and here is the reverse going back this way. So the reverse reaction is two molecules of sulfur trioxide as a gas will yield two molecules of sulfur dioxide as a gas and one molecule of oxygen. It's going in both directions. Okay, the forward reaction is going that way. The reverse reaction is going that way. That leads us to when this happens. A spontaneous chemical reaction happens when the reactants are mixed. So we put the two reactants together. The reaction goes in the forward direction, then the reaction also goes into the reverse reaction when the reverse reaction is taking the same rate as the forward reaction. Okay, when the rate of the reverse reaction equals the rate of the forward reaction, we have what we call chemical equilibrium. Okay, so we have reached equilibrium when the two rates, the rate of the forward and the rate of the reverse reaction, are the same. And that leads us to the equilibrium constant. You can see that equilibrium constant is abbreviated KEQ. Now, I want you to just be aware, I have up there in the green K sub C, because WebAssign has the equilibrium constant being K sub C. So I don't want you to be confused when you see that on WebAssign. I typically write KEQ, but WebAssign uses KC to mean equilibrium constant. All the equilibrium constant is it is the ratio of product concentration to reactant concentration, with each concentration raised to a power given by the number of moles of that substance in the balanced equation. So you're going to need a balanced equation, and you're going to need concentrations in order to calculate the equilibrium constant. And when we do so, this can be used. What capital A is it's the concentration of the first reactant. The lowercase a are moles of that reactant, so that would be the coefficient in front of the A. B is the concentration of the second reactant. The lowercase b is the moles of that reactant, which is also the coefficient. Once again, C and D, the capital letters are concentrations of the products. to the moles of the products. Now, does each reactant, or do we have to have a chemical equation that has two reactants? Absolutely not. It could only have one reactant. Could we have a chemical equation that has more than two reactants? Absolutely. Okay, so this is just a general form. Okay, it's just a general form. And when I use this general form, I can come up with the following. Whereas brackets C, okay, if I have the bracket with the C, I read that as the concentration of reactant, or excuse me, that would be product, the concentration of product C to the lowercase c power. The concentration of product D to the lowercase d value, which would be the number of moles. All over the concentration of reactant A to the A power, concentration of reactant B to the lowercase b value. So how am I going to set this up? How am I going to do that? You have the equation right here that's needed to calculate the equilibrium constant. How am I going to do it? Well, we're going to just go ahead and work example 1. So here's everything you're going to need for this example, and I'm going to pause my recording here a bit so that you can copy that down. Welcome back, chemistry students. We have dinitrogen tetroxide, N2O4, is a colorless gas, and nitrogen dioxide, NO2, is a dark brown gas. They exist in chemical equilibrium with each other. So you can see that I have my equilibrium reaction right here. I only have one reactant. I only have one product. My equation is obviously balanced. And it says a liter of gas mixture at 100 degrees Celsius and at equilibrium contains 0.0045 moles of dinitrogen tetroxide and 0.030 moles of nitrogen dioxide. So what I need to do here is I first of all need to set up my equation. So when I do so, when I write the equations for this reaction, I know that NO2, let me get that little, NO2 is to the 2 power. N2O4 is to the 1 power. Notice I put that 1 in there just so I make sure that I didn't forget. Yes, I did take into account how many moles of the nitrogen or the dinitrogen tetroxide I have. So those numbers, if I go back to the equation here, look, the NO2 has 2 in front of it. The N2O4 has a 1. So that's why I have those raised to that particular exponent, okay? So I have my equilibrium expression for this reaction. Now what I need to do is I need to perform my calculations. So if I know that here is my equation, I can go through and I need to calculate the number of the calculate the concentration for these. Now, I know that molarity is equal to moles per liter. Molarity is equal to moles per liter. And if I'm dealing with the very first problem, or the first one here, I know that they told me that I have 0.030 moles of this, and how much? I have it in 1 liter. So my molarity is going to be 0.030, capital M for molar. So when I bring that down here into my equation, I'm going to have my parentheses. I'm going to have 0.030 molar, and I'm going to put that to the 2 power because I got that from my balanced chemical equation. What is my molarity then for N2O4? Well, it tells me I have 0.0045 moles per 1 liter. So my molarity is going to be 0.0045 molarity and that's going to be to the exponent 1. So when I do my math, I come up with, let me go back, I come up with this equaling 0.20 for my equilibrium constant. Now, what does that tell me? What does the equilibrium constant tell me? I look at that, I say, well, great, it's 0.20. What does it mean, though? Well, this is what it means. As I look at these, all right, the equilibrium constant shows whether the products or the reactants are favored at equilibrium. Whether the products or the reactants are favored at equilibrium. If KEQ is greater than 1, then the products are favored at equilibrium. If KEQ is less than 1, then the reactants are favored at equilibrium. Well, I go back to my previous problem. I know that the value was 0.20. Is that greater than 1, or is that less than 1? Yeah, it is less than 1. So that tells me that for that particular example that we just worked, that the reactants are favored at chemical equilibrium. Okay. Now next we are Le Chatelier, which we will get back, or we will get into that later on during the week. So this has been the notes over equilibrium constant and reversible reactions. I'm Mr. Braun. Have a great day.